Hello, today we are going to discuss analytical vector addition. We've already done a little bit of work with vector addition, but the vectors that we were adding were pretty simple and straightforward and in one nice plane. So let me give you an example of what I mean by that. Let's say that you are in a car and you drive, 5 miles to the east. And then you turn around and you go 3 miles to the west. Whoops, wrong unit there, 3 miles. But then you decide that you want to turn around and you go actually 7 miles back east. We had discussed that you cannot, so I'm going to put this in red because this is wrong. You can't just say 5 miles plus 3 miles plus 7 miles equals 15 miles. That is incorrect because these vectors have opposite directions. So the better way to add these is to assign directions and say to the right is positive, to the left is negative, and then add these up. So 5 miles minus 3 miles plus 7 miles would give us 9 miles overall. All right, so what about if I instead say, you get in your car, you go 5 miles directly east, then you turn at an angle of 37 degrees and you drive for 4 additional miles. What is your resultant? Well, in math class, you might have talked about how there is the head to tail vector addition method, where if you want to add two vectors, you would draw them like we have done, where the second vector begins where the first vector ended, and their resultant is the distance from the tail of the first to the head of the second. You have to use graph paper and a protractor in order to do that, but it is possible. However, today we are going to learn how to do that without graph paper, but instead analytically, which means just mathematically and using your computer. All right, so a little bit of review. Yesterday, we learned that you can have Cartesian coordinates, so you can have an X and a Y value, or you can have polar coordinates, so you have a resultant with an angle. All right, and if you need to interconvert between these, let's say you have the X and the Y and you want to get to polar. So polar, the resultant would be equal to the square root of the X component squared plus the Y component squared. And the theta would be equal to the inverse tangent of our Y over our X. Then if you needed the opposite, so let me change colors here. Let's say you had the polar, but you need the XY, then the X component is going to be found by taking R times the cosine of theta, and the Y component is going to be found by taking our sine of theta. So let's see how to analytically add some vectors. All right, so let's draw an XY plane here. And let's say that you have one vector that is directed exactly along the x-axis, and it has a magnitude of 30 newtons. Then you have another vector, which let's say is up here at an angle of 60 degrees, and its magnitude is 20 newtons. Then we have a third vector, which we'll put down here in quadrant 3. We'll say this angle is 30 degrees, and let's give that a magnitude of 15 newtons. Now, newtons is just a unit of force that we haven't learned yet. So let's say that in real life, you had an object here in the center, and we had 3 ropes attached to it, and those ropes were described by these 3 vectors. What would be the total force acting at that point? You know, how do we add these up? That's very much like this situation right here. All right, so the first thing that you need to do is express all of these vectors using the polar coordinate system. So vector 1, we could say has a magnitude of 30 newtons. And since it is directly along the x-axis, we're going to say that it's at an angle of 0 degrees. The second vector, the blue vector, has a magnitude of 20 newtons, and it is at an angle of 60 degrees. Then this third vector, the yellow vector, whoops, hold on, let me get the right color. This third vector has a magnitude of 15 newtons, and its angle, all right, now yesterday we had talked about that it's really important to express all angles according to the unit circle. So they need to be somewhere between 0 degrees and 360 degrees in order to be helpful. So if that is true, we know from the picture that this is 30 degrees. Let me rewrite that a little more clearly. We shouldn't call that 30 degrees. We should say that that's 30 degrees beyond the 180 degree mark. So that's actually an angle of 210. Don't forget to express it that way in order for all of this to work out properly. Now, it would be really, really nice if we could just say, okay, let's add up our resultants, add up our magnitudes, add up our directions. But we can't do that. That would just not work out because we said that we need to take into account all of the different directions. So this is how you use analytical addition. All right, so we have to do this. Let's call this force 1 right here. I have to break force 1 into its x component and into its y component. All right, so the x component I can find by taking the magnitude times the cosine of the angle, which in this case is 0. 30 newtons cosine of 0 degrees should give me 30 newtons. Then to find the y component, I would take 30 newtons times sine of 0 degrees. That is going to give me a value of 0. Now, why is that 0? Well, that should make sense because if you look at the picture, this vector is entirely directed along the x-axis. So it should, all of its magnitude should be along the x-axis with nothing on the y. We need to repeat this for force vector number 2. So let's break f of 2 into x and y. All right, so the x component here is going to be found by taking 20 newtons times cosine of 60 degrees. And the y component is going to be found by taking 20 newtons sine of 60 degrees. All right, so when we plug that in, I get a positive 10 newtons for the x and a positive 17.3 newtons. Now we should always go back and check to make sure that makes sense. Should we have a positive x and a positive y for this vector? Well, yes, we should because it's right here in the first quadrant. All right, next we must resolve force 3 into its x and y components. So F3x, F3y. All right, we're going to take 15 newtons times cosine of 210 degrees. Then we're going to take 15 newtons times sine of 210 degrees. All right, for the x component, when I plug that in, I get a negative 13 newtons. And for the y component, I get negative 7.5. Do those values make sense? Should I have a negative x and a negative y? Yes, I should, because I'm down here in the third quadrant, which is negative x and negative y. All right, so we've done a lot of work, but we're still not there because we need to find what these would all add up to be. So why in the world did we just do all of this? Because we now can add the x components to find the resultant x, and we can add the y components to find the resultant y. All right, so let's do the x components here. All right, so the resultant x is going to be equal to the x component of the first vector, which is 30 newtons, plus the x component of the y vector, plus the x component of the last vector. So I have that is going to give us 27 newtons. Now I must find the resultant y component. So resultant y, I'm going to take the x component of the first vector, which is 0, the y component, the y component of the second vector, which is 17.3, and then the last y component, which is negative 7.5. All right, when I add those together, I get a resultant of 9.8 newtons. So what does this tell me? When I add these all together, my resultant vector can be described as having an x component of 27 and a y component of 9.8 newtons. That could be my answer. But what about if they said that they want you to express this in polar form? If we want to express this in polar form, then we've got to go back here and use these conversion factors. So the resultant overall is going to be equal to the square root of 27 squared plus 9.8 squared. Okay, give me a minute while I calculate that. I get a resultant of 29 newtons. And then to find theta, I take the inverse tangent, 9.8 over 27. And I get an angle of about 20 degrees. Now, before I certify that as truly being an angle of 20 degrees, I should go back and check to make sure that we are in the right quadrant. So if I went back and I plotted a positive 27 with a positive 9.8, that's gonna be in this first quadrant. Since it's in the first quadrant, a value of 20 does make sense because an angle of 20 would be right about there. So I could say that my overall answer is 29 newtons, comma, 20 degrees. What about if they wanted you to express your answer in rectangular form? Remember, that's the weird one that physicists use a lot. Okay, so if the Cartesian coordinates were this 27, 9.8, we could say 27 I hat plus 9.8 j hat, because the I stands for your x component and the j hat stands for your y component. So your takeaway lesson is, in order to successfully add vectors, you have to break them into their x and y components. So write what they are in polar form first, then break them apart into their x and y components, like what we did here. Then you may find the total sum of the x and the y in order to find the overall resultant. And that is how you perform analytical